Swayam Prabha. Digital India. Educated India.
Hello again, this is our second lecture on Gromacs software. What we have done so far is that we have told you what kinds of files are needed. For example, we started with a PDB file, we started with a top file, we talked of a GRO file. Now we will resume our discussion on the top file and then go to all other files that are needed, and then Sonanki will tell us how to actually run the Gromacs package. So you go ahead with the top file again.
Okay, so this is a topology file, and a topology file, as I have said earlier, it contains all the force field parameters, the Lennard-Jones parameter, which are sigma, epsilon, charge, mass of the molecule, how many number of molecules are being simulated. All these parameters are to be included in the topology file. This is a topology file for liquid argon. So here we see that the first three lines are comment, the line where it is written NB function, the NB function, it stands for non-bonded function, and if it is 1, then it means that we are using a Lennard-Jones potential, that is a 12-6-1 potential, and if it's 2, then it's exponential 6-1 potential. So it is,
sir, that 1 includes the Coulomb also.
Yeah, the 1 includes Coulomb also, and it is user specified. The kind of potential we want to use, we can specify it here. Then COM rule is the combination rule.
Right. That we will come when we come to water and other mixtures.
Yeah, because
And the last line is your, what is that?
Gen pairs, fudge LJ and fudge QQ.
Right.
It is used for polyatomic molecule and for triatomic molecule. For monoatomic molecule like argon, we don't use it. And then the second type is the atom type, where we have to define the type of atoms. Like here is just only one, that is argon atom. Then we have to specify charge of argon atom and mass. Then sigma and epsilon, sigma in nanometer and epsilon in kilojoules per mole. And all these parameters we will get from OPLS directory. The file name is FF bonded and FF non-bonded.itp. For each molecule and each atom, we have sigma, epsilon charge defined there. And for each different force field, the parameters will vary.
So when you say include argon.itp, in which directory will that be? Argon.itp?
It will be in the same directory in the working directory. Yeah, it has to be in the argon directory. And then we'll have molecules, where we have to define the residue name of the molecule and the number of total number of molecule or atom that is being simulated,
which are already chosen for a 30 angstrom or a 3 nanometer box length.
Yeah, that is 567. So it has to be defined by the user, and it has to be changed, and the residue name which is defined here, that is AR, it has to be same throughout. It has to be same in the PDB file, GRO file, topology file. It has to be same. Otherwise, it will give an error.
Suppose somewhere somebody writes A instead of AR, then what will happen? It will give some error.
It will give some errors saying that residue name AR not found.
Whatever the name,
Yeah, it will show the error.
Yeah, you can go to the next one.
So the next is we'll have a detailed description of argon.itp file. So we can open the file using the command vi argon.itp. This is the file for liquid argon. So here the molecule type, it is the directory where we have to give a detailed description of the molecule or the solvent or anything that we are simulating. Then in name, we have to write the residue name of the molecule or atom. Here it is AR, since we have used the residue name AR for liquid argon. Then there is NREXL. In this section, we have to define after how many bonds the non-bonded interactions are included in the molecule. Since this is a monoatomic molecule, it doesn't matter, but in case of water or methanol, ethanol, it has to be chosen properly.
So instead of 3, can I give 2 here or 4 here? Doesn't matter, because
doesn't
every pair is interacting.
And
what is that last line after the atoms?
After the atoms, I'll just say in this perspective, we have to define Nr. Nr is the serial number of atom in the molecule. Since there is only one argon atom, like
Okay.
argon is a monoatomic molecule, so serial number is 1. But if we have water, there will be 3 sites,
Okay.
so we'll have 3 serial number, 1, 2 and 3. Then in type, we have to define the type of atom in the molecule.
Okay.
In RESNR, that is the residue number. We have to write the residue number of the molecule. In residue, we have to give the residue name of the molecule, which we have used throughout. In atom, we have to write the name of atom name of each molecule. Then CGNR, this is the charge group number.
Okay.
Since there is it's a monoatomic molecule, the charge group number will be 1. Then there is charge, we have to define the charge of the molecule, and then there is mass. we
So
have to
this
write
mass has to be the same that we started with.
yeah.
So suppose this mass is slightly different from the original. It will take this as the final?
Yeah, it will take this as the final, because this we are including in the topology file,
Okay.
and this we are using in the simulations.
Now, what do you mean by atom type? What is the meaning of atom type?
Atom type, it will give a detailed description of the charge, mass, residue name, each and
Okay.
everything of atom. Then how many residues
so
are
for
there.
example, suppose I am doing something like benzene
Okay,
or say toluene.
okay.
There the charge on one carbon in the ring could be different from the
Yeah, so
charge
we
in
have
the...
we have to define each and every carbon atom there.
So there will be two types of carbon then.
Yeah, so in case of benzene, we'll have then 6 Nr. Here is Nr is the serial number of atom, right? So
Okay.
in case of benzene, we'll have 12, since there are 6 carbon and
But-
6 hydrogen.
Okay.
So we'll have 12 residues. Then each type of carbon atom will have a different charge.
Okay. So the type of atoms really means the total atoms then, not just the type.
Yeah, it means
Type plus the total.
total. Yeah,
So suppose I have something like fullerene with 60 carbons.
it will have
There
60
will be 60 different
type
carbons.
of carbon atoms.
Okay.
Yes.
And each one could have the same charge or they could
Or
have
they
different
could have
charge.
different charge,
Okay.
depending on the environment, single bond or double bond.
Okay.
So next we'll perform energy minimization of liquid argon. Since we started
Now, why do we need energy minimization?
because in PACMOL we started with a random configuration. We have just given a tolerance like the minimum distance between two atoms should be less than 3 angstrom or more than 3 angstrom or something, but this is not properly equilibrated or energy minimized configuration. So we need an energy minimized configuration to start with, so that we will get all the properties which we want to calculate from the simulation. It will correspond to a equilibrated configuration.
Okay.
So for energy minimization, we'll need an MDP file. MDP
But
file.
instead of minimization, in principle we could do direct simulation.
But
It
if
may
we,
not be effective.
it may not be effective, because if we energy minimize, we'll get a global minimum.
Okay.
We may not get a local minimum, but we'll get we'll get a local minimum.
Right. So
Instead of
maybe
a-
with minimization, if you go ahead, the chance of a successful simulation is much higher.
Yeah, and the properties like diffusion or
Right,
potential energy which we want to calculate will have a better value of that.
Okay.
So,
So is it like when students come to an institute, they don't know what it is and you give 1 or 2 days for orientation?
yeah, exactly.
Now this is like they orient nicely so that you can
Yeah,
do the
they
simulation.
orient nicely in the simulation box.
Okay.
So we
Say for
need-
example, if all the waters are in a strange arrangement, when you minimize, lot of hydrogen bonds will be formed. So it's a more
Yeah.
comfortable starting point for the
Exactly.
actual run.
Yeah.
Okay.
So we need an MDP file for this, and
Okay.
MDP stands for a molecular dynamics parameter file, and it contains all the information which is needed. So here is the information given. For energy minimization, we'll need em.mdp, em for
So-
energy minimization.
Now already there are parameters like Lennard-Jones parameter, charge
Yeah.
parameter, mass parameter.
Yeah.
So MDB file is having many more parameters than the old ones.
Yeah,
Like you are giving some, I see somewhere 0.01, that is a time step.
yeah,
Correct? So you will give many, so this includes more parameters than the starting one.
yeah, definitely.
So this is, let us say it is super file compared to the old ones.
Yeah, because it will contain information like which is the algorithm we want to use for
Correct.
minimizing the energy, then what is the total number of steps we require, then
So is this the last parameter file?
no, we'll have, this is just for energy minimization. Now
Okay.
to perform an MD simulation also we'll need a MDP file. That is a more,
Okay.
that is a even bigger file than this.
Okay.
Energy
So that will
minimization.
have maybe additional parameters?
Yeah, that will have some additional
Okay,
parameters.
so let us see what these parameters are.
So here the first line is integrated, that is steep. So that is the algorithm which we are using for energy minimization. That is the steepest descent algorithm.
Okay.
So
What
here,
are there some other types?
yeah, there is LFBG
Okay.
algorithm. There are different other algorithms, but for
So-
a simple molecule and
Right.
atom, steepest descent algorithm is fine to be like sufficient.
Did you use in your work other than steepest descent?
No, I have used steepest
This is
descent
good enough,
algorithm
right.
throughout.
Actually, steepest descent means you have a high energy level, low energy. It comes fastest to your lowest
Lowest
energy. So this is supposed to be a very good method.
Yeah. So the next line is EM toll, that is equal to 1000. So what is mean is that we need to stop minimization when the maximum force on one atom or molecule is less than 1000 kilojoule per mole per nanometer. So when the maximum force is 1000 it is reached, it will stop the minimization.
This should be between all pairs, isn't it?
Yeah, it should be between all pairs.
So starting forces could be 100,000, lakh,
Yeah.
it can be any number.
Because starting forces will be very high.
And is it possible that some starting forces will be so high that you have to reject the configuration?
Yeah, it may be a
Okay.
possibility.
So in that case, you have to do the pack mole once again.
Yeah.
Okay. Yeah.
So the next is the EM step, that is 0.01, that is the energy step size. So after 0.01 step it will perform again energy minimization. So this is a step size for energy minimization. Then
So this is not a time step.
no, this is not a time step. This is after 0.01 time frame it will, yeah, it's kind of a time step only.
Okay.
Because we are giving total number of steps, that is n steps is 5000 here. That is the
Okay.
maximum number of minimization step.
Okay.
So like suppose it started from the step 0.0, step 0, then it will go to step 0.01, then
Okay.
0.02. Like that it will perform the energy minimization. So next is NST list, that is the neighbor list which we need to update. So it can be, it is user specified, it can be between 1 to 10.
Okay. So for example, for liquid argon, could I have started with 5?
Yeah,
Huh?
yeah.
Okay. But
Then-
if it is molecule,
The preferred neighbor list is 10 for molecule, for water,
Okay.
for methanol. For
Okay.
polyatomic molecule, we prefer 10.
okay.
Then,
But in principle, there is nothing to stop me from taking 12.
no, there is nothing to stop, but
It will
generally,
take longer time to calculate.
yeah.
Okay.
So then is NS type, which is grid. It is a method to calculate the neighbor list, the neighbor of nearby argon atom.
Okay.
So we use the grid method to calculate it. Then is R list, that is the cutoff for the neighbor list, which is 1 nanometer. Then to calculate,
So that means anything which is beyond 1 nanometer is not the neighbor of a given atom.
yeah, we have to define the cutoff for neighbor list also.
Okay.
Then is Coulomb type. Coulomb type is for treatment of long range electrostatic interaction. We have to use certain algorithms. So here we are using particle mesh evolved algorithm, that is PME algorithm, to treat the long range electrostatic interactions.
So there are, instead of PME, there is what is called reaction field. There is what is called evolve. Maybe when we have time, we can actually do this, or we can give one as an assignment.
Yeah,
We
to
will-
check which is
Right,
more efficient.
correct,
and all.
correct.
Then there is R Coulomb. R Coulomb is the cutoff for short range electrostatic, that is 1 nanometer. Then RVDW is the van der Waals cutoff, which is 1.4 nanometer. And all this cutoff, that R list, R Coulomb and RVDW, it should be less than equal to half of the box length.
Correct.
Either less than the box length or equal to box length. It cannot be more than the box length. And then there is PBC, which is XYZ direction. That is a periodic boundary condition. It is applied in all the 3 directions.
So you said that all these cutoffs should be less than the box length.
Yes.
It cannot be more.
Or it can be equal to the box length, but it cannot be more than the box length.
So one of the reasons why we use cutoffs is that suppose there are 500 molecules, it is not necessary to consider the interaction of one molecule with all the 500, because whichever are very near it, like say a sphere of 1 angstrom, sphere of
1
1
nanometer.
nanometer diameter. So instead of 500, this will be around 250, and that 250 is enough to do the calculations. We
Yes.
need not consider all. So this is just to increase the speed of computations.
And also if we start calculating between 500 atom, it will take
Much longer.
much long time, and then
Correct.
computation
And
space
plus,
will also.
many of those computations are wasted, no?
Yeah,
So
exactly.
it doesn't matter, we can do all the calculations if they are really needed.
Yes.
But if it is unnecessary, one should cut off.
Yes.
Okay. Yeah.
So this is the MDP file that we will be using for energy minimization.
Okay.
So now to perform energy minimization, we need an TPR file, which is a binary file, and it will contain GRO file, topology file, and MDP file.
Okay.
So these are the three files that is contained in one single em.tpr file. Now to generate em.tpr file, we have to type the command grompp space -f em.mdp space -c conf.gro space -p topol.top space -o em.tpr space max1 space 2. So grompp is a command which will combine the MDP, GRO and topology file into one single binary input file, which is a TPR file.
So that is your -o refers to the output.
-o refers to the output, and -f, -c, -p are the flag for different file. And
Okay.
if we just type grompp space -h, which is the help command, it will display that what is the flag that is required before an MDP file, before a GRO file. So one need not need to memorize the whole command like grompp -f em.mdp.
So
one will get if they
after
just type.
practice, you will know all that.
Yeah.
But now, do you mean to say all the four will be needed in this?
All the
MDP, GRO, top and
MDP,
TPR?
GRO and top, these are the main input file that
Input.
is required, and we will use all these three file in one
generate?
to generate a TPR file, and grompp is the command to do that.
Right.
And in that single em.tpr file, it will contain information of all the three files.
So that is the final thing that is needed to do the energy minimization.
Yeah, this is the final thing which we'll need to do the energy
So now,
minimization.
suppose instead of maximum warning 2, I
Yeah.
give 5.
Doesn't matter.
Suppose I give 0.
0 it won't take, because 0 if you give, then there is no point of giving the max1 command. Max1 command is basically that sometimes while running a simulation we get warnings.
Correct.
And warnings you can ignore.
Okay.
So we generally get 1 or 2 warnings, so that is max1 2 we give. Or but
Suppose I don't give that command at all, max 1, 2, then what will happen?
then
It will still work?
yeah, it will still work.
Okay.
If you get warning, say sometimes while running the command grompp, you get warning like there is one warning, there is 2 warning. So to ignore those warning, we use max1 command, because those warnings are not so important to consider.
But are these warnings because when the force is very large, for example?
Not exactly the force is very large, but sometimes like this algorithm is not working for this molecule, we need to
Okay.
use different algorithm. But if it at all doesn't work, it will give a segmentation fault.
Okay.
But warning we can ignore.
Okay.
Segmentation fault we can't. So now we'll get a.
But then segmentation fault is not a warning.
No, segmentation fault you cannot even run it.
That means it will just crash.
It will just crash.
Okay.
You have to properly rectify and identify what is the
Right.
error,
Okay.
and then only it can work.
Right.
So we combine all these three files using grompp command to generate em.tpr file.
Right.
And then since it is a binary file, we cannot view it using vi command.
Right.
So we have to have a different a command to view this file. So gmx dump is the command. So you just type gmx dump space -s space em.tpr and then enter.
So what this GMX dump does, it reads the binary TPR file
Yes.
and writes the output on the screen.
Yes.
So is there a way to write the output not on the screen but into some file?
No. Or you can open the TPR file using a text pad.
Okay.
So it will
But
give
then
all
it-
the detail.
Text pad will give you too much information.
Yeah,
no?
it will have all. It will have the GRO file first, then it will have the topology file, then it will have the MDP
So
file.
suppose I do gmx dump -s em.tpr
Yes.
-o something. Maybe I will be able to write it on some file. We can try that.
Yeah, we can try that, but we cannot read the TPR file.
Correct. No,
using-
I am not saying you are using gmx dump.
Yeah, yeah.
The default is dumping on the screen.
Yes.
Now it should be possible to dump somewhere else so that I can see it at leisure.
Yeah, maybe.
Okay.
Maybe we can try it
Right,
using
right.
-o command.
Correct.
So, yeah, given the detail like that -f flag -f, it specifies the MD options unit.
Okay.
-p will specify topology file unit.
Right.
-c is for configuration. -o is for output.
Okay.
Now
so that
after
configuration is what file? GRO file?
yeah, GRO file.
Okay.
So after we type the command grompp -f em.mdp, something like this will appear on the screen.
Okay.
Right?
So there is one warning in
Yeah,
that
there
case.
is one warning,
Okay.
so you
That is
can
okay.
ignore it. Yeah, that is okay.
And what are all those commands? The universe is something.
Yeah, that when you run a command in Gromacs, you will always get a quote.
So no, that is just for some humor.
Yeah, that is
So
just
that
for some humor.
you don't get exhausted.
Yeah.
Okay.
So now when
But we cannot change those.
no, we
comments.
cannot change it.
Okay.
It comes automatically.
Okay.
Now
But
to
it is not
perform-
automatic because somebody has put all those
Yeah,
comments.
somebody has put.
Right. Okay.
So now to perform energy minimization using the TPR file,
Okay.
we need to use the command mdrun.
Okay.
So if we type mdrun -h, we can get we can have a look on what it does.
Right.
So
Details of all the options.
detail of all the options. So this
Okay.
is the full command that you have to type on
Right.
screen
Huh.
to get the output file from mdrun. But instead of using such a long command, we can as well use mdrun space -v space -deff_nm space em. So it will create all the output file using initial as em. So it will create em.trr, it will create em.gro.
Okay.
em.gro is the energy minimized configuration.
Okay.
Then em.edr is the energy file. It contains all the information about energy like potential energy, kinetic energy, temperature, pressure. It will contain all the file. em.log is the energy file in a log format. Then em.xtc is the trajectory file. At each time step, what is the position, coordinate, velocity, it will contain all those information.
So now how do I know that this MD run is only minimization and not final dynamics?
Because we are using the TPR file of energy from energy minimization.
Okay.
So if we use TPR file of full MD,
Right.
then we have to type md run space -v space -deff_nm space full.
Okay.
Since we are using EM, which is
Yeah.
the TPR file from energy minimization, so it
Right.
will give us the output of energy minimization.
Okay.
This is the command which we can use instead of the large command previously. It will get the same output.
Okay.
So now after energy minimization of liquid argon, we will see the following lines where it will write the tolerance, number of step, and then steepest descent converge to F max less than 1000 kilojoule per mole per nanometer. In how many steps it is getting converged, then what is the potential energy, what is the maximum force on which atom. It
Right.
will give us all this. And now we will have the lowest energy configuration in the form of em.gro.
So now our limit for the force was 10 to the 4.
Yeah,
Correct? Now this is saying maximum force 10 to the 2.
yes,
So that means it did better than what we expected.
yes.
Correct? So instead of 10 to the 4 for the maximum force, we could have given 10 to the 3 also.
Yeah, but maximum 10 to the power 4 is used because in case we have a large
Right,
molecule or large system.
Right.
So
So
in
now
that
other
case,
thing that is noticed here is that you did that only 17 steps are used.
yes.
Okay.
And I have given 5000 steps.
But the potential energy is still positive, no?
Yeah, it is positive. In case of neutral molecule, it generally comes as a positive quantity.
Okay. But that 10 to the 2 is not a very large number.
No.
Not a very
But
large
when
number.
we do for charged molecules, say
Right.
water or ions and all, will get a negative value of free.
Okay. Because if it is not negative, then you cannot really start there.
Yeah, because in case of neutral molecule, it's generally found to be positive. But
Okay.
if we have a charged molecule, we'll get negative quantity as
But
well.
instead of 10 to the 2, suppose it was 10 to the 4, then you may have to minimize again.
Yeah, then it won't get even minimized. It will show
Okay.
us error that F max didn't converge to the.
No, F max could be small, yet the potential large. Can that happen or not? Generally not.
Generally not.
Okay, because if the force is small, the potential is also small.
Yes.
Okay.
So now we are having the em.gro file, which is the energy minimized configuration file.
Okay.
And now taking this configuration file, we'll start our full molecular dynamic simulation.
Okay.
So in full.mdp file, we'll have all these detailed thing. So I'll just give a brief information about all
All
this.
the parameters.
Yes. So integrator, in the first line we'll have integrator. Integrator is given as MD. MD which specifies that which is the algorithm that we are using to integrate Newton's equation of motion. So here we are using leapfrog algorithm. There are many other algorithms, Worley algorithm,
So there are some
velocity Worley.
Runge-Kutta methods,
Yeah,
gear
there are
algorithms.
different methods. So
Tens
in
of
that
algorithms.
case, we have to use a different
Notation.
different notation.
Right,
In case we are using MD, which signifies we are using leapfrog algorithm.
Okay.
Then DT, it is the time step of MD simulation, and it has to the time step is generally taken as 2 femtoseconds. Then is NST x out, which it is equal to 100. It means that it will save the coordinate of the particle after every 100 into dt time step. Then
So now why do you think we need this 100? Instead of 100, suppose I did 1000, what will happen?
it won't happen anything, but
You will write much fewer coordinates.
it will write much fewer coordinate, but
Okay.
if we need to analyze very carefully and if we need to get good result, it's better to have fewer, like get the coordinates and velocities saved after fewer number of time steps.
Okay.
Then is NST V out is 100. It means it will save the velocities of each particle after every 100 into dt time.
So that NST out and NST V out,
Yes.
X out and V out, they can be different?
100, suppose you are giving 100 as X out and 200 as V out.
Right.
Yeah, that is user defined. It can be different.
Yeah. See, that is, suppose you don't want too much information on velocities.
Yeah.
Then you may give that NST V out as a very large number.
Yeah, you can give it at 10,000, but it has to be less than the number of
Number of
steps
steps in
that
the
you are.
simulation.
Yeah.
Right.
Then there is NST F out. It will write the force on each particle after every 100 into dt time step. Then there is NST log. The energy of the system will be written in a log file.
Okay.
Then there is NST XT CO out, that is 500.
Here, your NST log, it is showing 90,000.
Yeah, because we don't
Whereas
need.
on the right side, it is 9,000 times dt.
I
think.
guess it will be 9,000
Okay.
times dt. It's
So-
a typo.
Okay, so both should be the same.
Yeah, both should be the same. Then the next file is.
But the more important is the NST log value, not what is written on the right side.
No.
Okay.
Then is NST XTC out, that is 500. It means that the trajectory of the whole system will be written after every 500 into dt time step. Here also there is a typo. It has to be 500 into dt, not 9,000.
Okay. That's
So,
okay. But
and-
main thing is your bold-faced values. These
Yeah.
are the parameters.
And every, like, this trajectory file is very important. So
Okay.
lesser the number, better we get the result.
Correct.
Then NST list is the neighbor list, as I have already said earlier,
Okay.
which is used to make update the neighbor list.
Okay.
Then NS type is grid, that is it will calculate the neighbor list using the grid method.
Okay.
Then Coulomb type is PME, that is the long range electrostatic interaction will
Particle
be.
mesh evolved.
Yeah.
Right.
Then we are using Coulombic cutoff as 1 nanometer. And PME order is the interpolation order for the electrostatic interaction, which is taken as 4. Then there is van der Waals type. Here also we are using cutoff for van der Waals interaction, that is 1.5 nanometer. Then there is T couple, that is the temperature coupling.
Okay.
So we have to, since we are performing simulation in NPT or NVT ensemble, so we have to fix the temperature. We have to keep it constant throughout the simulation.
So if there is any fluctuation for some random reason, it will rescale to a temperature of our designed
Yeah.
value.
So we are using here velocity rescaling thermostat to
Okay.
fix the temperature of the system.
Right.
TC groups mean temperature coupling group. So here you can specify which are the group that you need to couple or you need to fix the temperature of. So here we are
So for
fixing
example,
the
I have water. I need not use hydrogens. Is that what you are saying?
No, system is like you have water and methanol,
Okay.
right? So you have to fix the temperature of water and not methanol. So you can specify water as different temperature coupling group. But generally we fix the temperature of the whole system.
Correct.
That is what is desired. Then
Right.
there is reference temperature, which is 298. So
To
that,
which all things are scaled. They are all
Yes.
scaled to 298.
yes, and then there is constraint.
Right.
No, that is because here we are using just monoatomic
Right,
molecules,
right.
so we don't need to fix any bond length or bond angle. And then there is P couple, that is Berenson. So we are using pressure
pressure.
coupling.
Okay.
Yeah, Berenson algorithm is being used,
Yeah.
and P couple type is isotropic. That is it is taking as isotropic system. Then tau P is the pressure coupling constant,
Right.
which is used as 4 picosecond. Then compressibility is 4.5. It is in bar,
Right.
per bar inverse.
Right.
Then reference pressure is 1 bar.
Right.
And gen velocity means it will generate velocity using the Maxwell-Boltzmann distribution.
Okay.
So these are the parameters that is specified in the MDP file.
Right. So now the next command is for your actual MD or minimization.
We have already done
Done the
minimization.
minimization,
So
right.
next command will be for full MD.
So we will just show the command and conclude this lecture. Okay.
So we have already em.gro, which is the
Right.
energy minimized configuration,
Right.
and then we'll have full.mdp instead of em.mdp.
So this is the command to do the final MD simulation.
Yes, it is the
Okay.
same command as em.mdp.
Right.
Just instead of em.mdp, we will be using full.mdp.
Right.
We'll be using the output gro file of energy minimization, that is em.gro.
Okay.
Topol.top file is the same.
Is a common.
Yeah, it's
Right.
a common. And then output file here we are giving us full.tpr instead of em.tpr.
So the max one here need not be the same as earlier. It could be different.
It could be different.
Right.
And now we'll be doing MD simulation using the command mdrun
Right.
space -v space -deFFNM full.
Right.
Full is the TPR file that we are getting from the
Okay.
GrowMPP command.
So what we will do, we will conclude this with this MD run statement, and next time again we will begin with MD run and then analyze all the trajectories, and if there is time we will also do the installation. Okay? Thank you.